Alright, welcome back. So in the last video, we were just talking about the general overview of an ANOVA and general linear models and sort of what the goal is, right? So instead of comparing two groups with a t-test, we're going to be comparing more than two groups with an ANOVA. First, just to tell us whether or not there are any differences within the big picture, and then I'll show you what to do after that. So let's get into it with an example. Okay, so you're becoming super famous. You're making a ton of money as a bona fide statistician. You've done t-tests, and everyone knows how famous you are, right? Okay, and then somebody comes up to you and says, okay, I have this research study where I've got 40 rats, and I've got 4 different types of diets that I've put them on, and I want to see which diets are different from each other, which diets are statistically significantly different from one another, right? So we've got these 40 rats, and we're measuring their weight, okay? And I think that's in grams. So we're measuring weight in grams, and we want to see how the weights differ between these 4 different diets, okay? And the diets are distinguished by the amount of protein and where the source of that protein is, right? So we have a low and a high amount of protein, and they can either come from cereal or beef, okay? So four different diets. In fact, instead of me just fumbling through it, let me show you. So ignore this just for a second, but we'll come over here, right? We can kind of see what's going on, right? So we have our first diet, high protein that comes from beef. And then we have our second diet, low protein that comes from beef, and then high protein that comes from cereal, and low protein that comes from cereal, okay? The details herein are not totally necessary because we're just getting the idea of an ANOVA. We're not getting into the biology of this whole thing. But we can kind of see that within each group, there are 10 rats in each group. That means that the total number, right, would just be 40, right? So our total sample size is 40 with 10 in each group. It helps to have, even numbers in each group, but they don't have to be. Very similar to an independent t-test, right? This is helpful, but not totally necessary. Okay, so let's answer this question down here. How many factors do we have? Well, like I said before, right, we just have one categorical variable, and we can translate that back into our kind of stats talk, which means we have one factor. We have one qualitative variable, one categorical variable, okay? And then how many levels do we have? Well, within this factor, how many groups, right? That's essentially what we're doing. We've got 1, 2, 3, 4. We got 4 groups. So let's call that K groups. So we got 4 of them, right? So let's say this is just the number of levels / groups. Okay? One factor is diet, and within that, we've got 4 different things, right? Okay, cool, no doubt. So then we come over here to our 5-number summary with the mean in there of weight, okay? But this is the 5-number summary for the whole column of data, for the full 40, not being divided by any of these groups, right? So this is the 5-number summary for all of the data. What if I want the 5-number summary for each one of these groups, right? So the mean, median, min, max, and the quartiles, right, for each one of these things, right? This is for the whole picture, right? We need to kind of see the general idea for each one of these groups, right? So we don't have to do that by hand. I've already done it for you. So this is what you'll see on the test and in real life too, where actually I just put the mean and the standard deviation. That's okay. We've got other examples here coming up with a bit more, but now we see then that we've got the total mean, the total group mean is 87.25. Let's write that. So we'll call this X bar for all of the groups, right? 87.25 grams. Okay, now, and we'll actually put we don't have the standard deviation. Okay, so we'll just leave it as this, right? Now already we can kind of see the over and under, right, between each group. So let's see, our beef with high protein, right, their group mean was 100 grams, right, which is above the overall mean, right? The group, the low protein, 79.2 grams, well, that's below the overall mean, right? And we can kind of see here that the cereal, both of the cereals, right, the source of protein, that's pretty close to the mean in both of them, right? Okay, so I can, we can already sort of see what's going on here, right? Some of these groups do have a higher group average, and some of them are lower. In fact, all of these are, right? So we got some sleuthing that we got to do. We got to figure out what's going on here, right? We got to figure out if this difference from the overall mean or this difference from each other, right, is statistically significant. So maybe we can get an idea here that this beef and high protein might be different than this beef or the low protein in the cereal, right? So already we're getting kind of close. Why don't we make some box plots? Well, you don't have to. I will. So here it is, right? I'll zoom in here just a little bit too. So we've got our 4 different box plots, and we see that there's a bit of overlap, right, between these kind of 3 here. This might suggest that there is no statistically significant difference between these 3 groups. But look at this one. This one kind of goes above and beyond as far as the median goes and sort of everything above it, right? That half of the data. That goes quite above all of the other data, right, that we see here. So we might have evidence, or at least this figure here is suggesting that this beef with high protein, right, might be statistically significantly different than these other 3 groups, right? We'll have to test it because we don't know. We don't have enough evidence to say, really anything. We're just suggesting. This figure is suggesting that this might be statistically significantly different, right? We still have a little bit of overlap down here with all the other data, but who knows, right? We might have to, we'll definitely do some more sleuthing here. Okay, so we got this grouped summary. We've got these box plots that we're used to seeing, right? So let's kind of see what's going on, right? So you really do not have to understand what's going on here. This is computer code. This is R code. And at the beginning of the semester, I said that we were going to be doing some stuff in R. I kind of changed my mind, just because it's not worth adding that on your plate. I'd rather just you understand the concepts, right? So this is what you would see if you're doing it in a different stat class, right? In a sort of higher up stat class. But what is happening here? Well, this is an AOV function, whatever. This is just saying, hey, make a model out of this stuff, right? And we want to essentially just take a look at this, right? We can ignore where the data. This is just saying where the data came from. But let's check this out because there's some interesting things going on in here. I've got sort of the English translation, but let's just focus on this component right here. This can be translated into weight as a function of diet, okay? So what this is saying is that we're saying, okay, diet has some influence on weight, or at least that's the way that we want to model it, right? Weight is a function of diet, right? Or at least that's what we're trying to model here. We're trying to get the computer to do everything for us, right, based on these 2 things, right? So this is how we think the world works, right? We think that weight has some function of diet, right? Or diet influences weight in some kind of way. And that's what we're doing all here, right? So this is going to make that ANOVA model for us. Thank God. Okay, all right. So here's sort of the nuts and bolts of what's happening on the inside of an ANOVA. If you're not interested, honestly, out of all the things, that is okay if you're not interested in this. But if essentially what it's doing is that we've got our data, right? This is very similar to a box plot, except it's just the raw data, right? So each point represents one rat, right? So we've got some rat up here that's like 119 grams, one rat that's down here that's like 70, right? And we can kind of see so on and so forth. Now what an ANOVA is doing is that it's comparing each data point to its own mean, which I've got here, right? So like this, it's essentially just drawing a bunch of lines. I'm only going to do it for this one, right? And it's seeing how far away each data point falls away from its mean, okay? Within the group, right? So it's going to do it. It's going to do it down here too, right? Same kind of deal, right? So that's one component of the ANOVA, and then also it does a bunch of fancy math that we're not going to worry about. Compares each group mean to the overall mean, which is right here. So this is the group mean. Okay. Right. All right. So does that. Does this kind of close, right? And then it does a bunch of ratio stuff that we're not going to worry about. And then it spits out essentially a summary statistic for that whole big fancy thing that it just did. Okay, so that's the general idea. So we see here that the beef with the high protein, the mean, its mean, this group mean, is above the overall mean, right? With all of the groups. These three are below the mean, right? So we have maybe a little bit more evidence that this group is going to be way different, right, than these three here. Because this one is way above the overall mean, but it's also way above all of the other ones too, right? That's the general idea, okay? So that's the anatomy of it, the very generalized anatomy. Don't worry about it, honestly, because we're getting R to do everything for us. Okay, so what does it spit out? Well, it spits out this. This is what the ANOVA model looks like. Now, out of all the things that you see on here, what do you really need to worry about? Well, let's see. I think, yeah. Let's do it like this. We care about the degrees of freedom, okay? DF should be pretty familiar. We don't really care about, don't tell anybody I said this. Don't care about this. Don't care about this column, right? So this is just dividing everything. We kind of care about this, kind of. And then we big time care about this, okay? And so let me, instead of just saying this and this and that, let's define what each one of these things are. Okay, so we've got two different things here. We've got our diet, right? So this is all of the information based on those four groups, right? Protein groups and where they came from, okay? So this is all, you can essentially divide this in half, right? And this is all regarding the diet, right? All of this information is all oriented around the diet. And then we have this idea of residuals, right? And so remember that when I was saying what models do is that it puts the data into two things. We have our model, and then we have our error, okay? This is the model component, and this line here is the error component, okay? So that's just our two different sort of partitions that we've got, right? Or two different piles that our data are in right now in this form, okay? So we've got degrees of freedom for both of these things. We've got degrees of freedom for both of these things. So we have degrees of freedom for the groups, right? So this just represents the different diet, and it's just k minus 1, or the number of groups minus 1, okay? So we had 4 groups. The degrees of freedom, right, once we calculate a bunch of means, are going to be 3, okay? Oops. And then for the error, for the residuals, right, the error, we can even just say this, right? Same thing, just being fancy. it's the number of groups minus the total number of data points that we have, right? And we see that for the error component, we've got 36 degrees of freedom. Now, before we go on, you might think that error is a bad thing, and it's not. In fact, a lot of statistics is sort of based around this idea of what isn't being told, right? And we've been doing that kind of in the background too with these t-tests, right? And these z-tests and all this stuff, right? So this is not bad, right? Having error is not a bad thing, okay? It is not a bad thing. Okay, so we've got these two components here with their own degrees of freedom. Number of groups minus 1, number of groups minus the number of data points we've got, right? So a little bit of algebra there if you wanted to do that yourself to figure out the total number, right? Okay, what did I say? I said to ignore the sum SQ. That's just the sum of squares. Who cares? The mean SQ, no, we don't care about that either. But we do care a little bit about this F value, okay? Just like in t-tests where we were calculating a t-statistic, right? We're doing the same thing, but we are calculating a different type of test statistic, and it comes from a slightly different type of distribution. I'm not going to have you plug that in anywhere. I'm not going to have you do really anything with it, other than knowing it's the same sort of concept, right? That just tells us how far away our data are from where we expect it to be, right? So instead of a t distribution, this F statistic comes from the F distribution, blah, blah, blah. Looks like this over here, where it also changes based on how many degrees of freedom we've got, right? Except it changes as a component of both degrees of freedom. So the degrees of freedom for the diet here, the group, is one component of this curve, and then the other, the degrees of freedom for everything else that's left over, right, the error, is another component of this. Not totally important because we're not going to be, really getting into the weeds here. But it turns out that this F statistic is actually just the square root of a t-stat. That's more of a fun fact than anything. I won't ask you anything about that because there's a little bit of finagling that goes on here too. But just something, right? This is all very much related. It's crazy. It is crazy. Now, if we go back here, care a little bit about degrees of freedom, care a little bit about the F value, but check this out. We care a ton about this. And what is that? Well, the PR greater than F, right, is just the probability, right, that our test statistic is in or outside of our rejection region, right, where it's very similar to a t-stat, except in this case, it just gives you the p-value, right? So same rules apply, right? If it's less than alpha, then we have significant evidence against the null hypothesis, right? Okay, so in this case, yeah, actually, let's go into the next one. So we have our p-value here. Our p-value, it's right there, equals 0.023. You can ignore the significance codes for now. They just sort of help your eye get there faster, so you can see if you're comparing a ton of different things, which we're not in this chapter, at least. Ouch. Sorry. In this chapter, we're not going to so much worry about it, or in this week. But this is just to help you kind of organize things. But this is our p-value. This is what it actually equals, okay? So how you would interpret this is that since p equals 0.023, and, we see here that p is less than 0.05 by a bit, we have significant evidence that the means of all diet groups are not equal, okay? So we're saying that based on this, we can actually look at it too. Look at this one, right? Zoom it in just a little bit, right? We have significant evidence that based on this whole big picture here, that at least one of these groups is different from the others, right? That's what we're saying. That is what we're saying. And it might be, we might be looking at this one, right? Okay. Very cool. Very cool. So we have a significant p-value, right? If you needed to look at anything on here, right? If you only needed to look at one single thing, it's this, right? For this class, at least, okay? So this is our p-value, answers this question, or can be interpreted in this way. Okay, but with this, we've got some room, we've got more room to kind of wiggle and make a big mistake, right? There are some assumptions with an ANOVA that we have to meet. I'm not going to so much worry about it in this class because I'll give you kind of picture perfect examples. But in real life, you got to check one thing, right? And in this case, it's those residuals that we were talking about, or the amount of error that's in our model. Okay. So if I go way back over here, way back, and draw these lines again, right? So we've got one that goes like this, right? These are all distances away from the group mean, right? This is all distances away, and we can do the same thing too with each data point and the overall mean too, and then the means of the group to the overall mean, right? That's essentially sort of that combination of things. There's a ratio there that is being done in the background, right? But these distances here, well, these are just values, right? These are just some numbers, okay? And so we can record all of those numbers, and we'll call those residuals, okay? That's where this is coming from, right? All right. So when we look at these residuals, we want to be able to plot them, okay? We want to be able to plot them. And we can pretty easily, and again, the computer will do this, so you don't really have to so much worry about anything. But we can plot this difference between what we have and what is predicted or what is expected, right? So what we've got minus what we expect is this idea of a residual, okay? And we can do that for every single data point, and that's going to be some new value. And we can plot these like so, okay, onto a histogram. But before we kind of get into that anatomy, we use these residual, let me write this, residuals plots, or plot. We're going to use a histogram. We're going to use a histogram to figure out how adequate our model is, right? So essentially, we're just using these residuals to determine whether the data are normal-ish, okay? Or include outliers, right? So essentially, how normal our histogram looks of the residuals, of the errors, right, in our model, then the better, right? So the more normal, the better. So we want to look for, effectively, a seemingly normal distribution. Now, in real life, people are pretty slack about this. And I am guilty of it too. It's totally, convention to be as strict or as slack as you want. There's plenty of other tests to test for normality, but most people, if they do anything at all, just look at a histogram. That's what we're going to be doing in this class too. So this is the histogram of those errors, the distance away from what we've got and what we expected it to be. And if we were to trace a line kind of over like this, we get a decently looking histogram, a decently looking kind of density thing with this line. Some people would maybe argue it's a little bit, left skewed. I think that this is fine, and it's all about experience too. As you get more and more experience with looking at these kind of things, then, great. You're able to kind of pick out normal distributions a little bit better. But if you think about it, if we were to get rid of this bar, this big tall one here, and maybe if it were to be more or less down there, then this thing would look pretty normal. With this one big bar up there, maybe a little bit left skewed. In this class, I'll always give you kind of a textbook picture perfect example. But it is always good to look at the residuals and make sure that they are normally distributed. Because if they're not, then that means we might be overestimating with one group and underestimating in another, right? With our estimated differences, right? Okay. But right now you're probably wondering, what the heck? What the hell? So we are able to, gosh, I think I just had an aneurysm there. We are able to say that, yeah, I think that we can trust this model, right? What we found here, where we found that we have significant evidence based on this p-value that at least one of the groups is different than the other ones, right? But we don't know which ones, and we don't know by how much. This only looks at the big picture. The ANOVA only looks at the big picture. Okay, so you're probably wondering who this is. This is Ronald Fisher. He came up with the ANOVA, right? And then back in that day, he said, okay, once you figure out that their big picture is at least one group that's different, go in and do a ton of t-tests, right? For each combination of groups that you can get. However, that takes a long time, even to do it by, with small data sets, doing it by hand. If you have 6 or 7 different groups in there, even with 4, like that's still kind of a while, right? So that's one reason why maybe, I don't know, maybe he just gave up. I don't know. He's super smart, or was super smart. Pretty cool looking beard too, just this whole look. But also there's another idea that the more comparisons you start to make, the more likely you are to make a mistake, right? To say that there is a difference when there really isn't, right? So we've got some additional tests that we can do, right? So essentially what we're going to be doing is just a bunch of different t-tests, right? But we're going to be correcting for a few things, right? One, we're going to be correcting for the number of comparisons we're making, right? Because the more comparisons we make, the more likely we are to make a mistake here and there, a small mistake, where we say something is happening, but it's really not, and that's okay. And we've got 3 different methods. But for this class, we're just gonna go over the one, right? Because it gives you the most information, and it's it's pretty simple to kind of see. We're gonna be doing the Tukey's honest significant differences. So developed by this guy, John Tukey. Cool dude. I think he's still alive too, which is great for him. But you also hear about Bonferroni corrections. This dude is a lot older. He is an Italian, or was an Italian economist. Pretty cool. And he made up his own way of doing these t-tests, essentially, after doing an ANOVA. And we have false discovery rate, frequently just called FDR. It's not actual Franklin Delano. It's something else. But we're just going to be worried about the THSD test, okay, or Tukey's honest significant differences. And it looks something like this. Ugh, gross, right? So we've got within this a few things that we don't need to worry about. This is just saying, this here is just saying what's going on, right? Multiple comparisons of means, right? That's what we've been doing this whole time. With t-tests, we were only doing one comparison of the differences of means, right? In 2 groups, essentially. And now we're just doing it with a bunch of different groups, okay? And then we can specify the confidence level too. We'll stick with 95 because that's what we've been doing this whole time. And then, we won't worry about this or anything. This is just telling us what our model is. Okay, but we do come down here to what actually matters. So let's take a look at the anatomy here. So in this first column, and I'll kind of divide it up like this, just so you can kind of see, right? In this first column here, this is just the difference between every possible combination of groups, okay? So in this case, we've got beef with the low protein minus the beef with the high protein, or the differences, right? So this is just the column of differences. Okay, easy peasy, right? Easy peasy. So there's no way that you can kind of control the order in which it does this math here. But actually, let me come over here. This is group differences or group comparisons. So this is saying what group is being subtracted from the others, right? And then we get this column here that is the actual difference. So it's the difference in means, right? So here this would be maybe like x1 minus x2, right? That kind of situation. This is what's going on for this one, so on and so forth for all the other ones, right? And you can read it just straight across the line. But here, in this next column, is the actual difference between these two, right? So the mean of the beef with low protein minus the mean of the beef with high protein is negative 20.8 grams, okay? On average, right? So that's just looking at the average difference, or the difference between the two averages. The difference between the two means, if we're being very specific here, right? And so since this is a negative number, if this ever shows up as a negative number, that means that this group here is larger, right? So put simply, 1 minus 2 is negative 1. That's what's happening here too, right? Okay, and then we get over here, we get a 95% confidence interval for that difference, okay? With the lower bound and the upper bound. Okay, very cool. So we'll come back to that in just a second. But then we get this. This is our p-value, right? It's essentially the p-value that gets spat out after you do a t-test, right? This is doing all of the work for you. So all you really need to do, straight up for the test, is take a look at the ANOVA output, see if the p-value there is statistically significant. And then go on to the next page, whatever it may be. You'll probably see something that looks like this. Then you go over and see, okay, here's all of the t-tests, essentially, that are happening. What are the p-values associated with each comparison, right? And then you come down here. Come down here to this column first, if you want. Find all of the p-values under 0.05. And then you can make some interpretation, right? So let's actually go on to the next page. And it turns out that the only statistically significant difference between these groups are between the beef with the low protein and the beef with the high protein, okay? So we have, whoops, what's on the next page? Oh yeah, okay, cool. So based on the ANOVA, we have significant evidence that we've already said that there at least one group is different, okay? Is different from the others, right? Okay. And then based on this Tukey's honest significant differences, we have significant evidence that, let's see, beef with a high protein is statistically significantly different than the beef with the low protein, okay? And that's that, right? And then we are 95% confident that the true population difference is, oh boy, between... Now, depending on how you want to, put this in a different kind of frame, you might say that beef on average, here in this sample, beef with the high protein on average was 20.8 grams larger than beef with the low protein, right? Or heavier or whatever. It always helps to kind of come back to these pictures. Come on, boy, good Lord. These pictures, right? Just to kind of help you orient yourself, right? So we see that the beef with the high protein is larger than the beef with the low protein, right? So that's essentially what's happening. Okay. Oh boy, so we come all the way back here. We're 95% confident that the true difference, right, the true population difference is between 2.78, let's see, 2.79 grams and 38.81 grams, right? And I'm just getting that from here, right? And I'm just switching this around to make a little bit more sense, because it doesn't, at least to me, I don't like to see, negative numbers, especially when we're talking about differences. It's kind of hard to, interpret sometimes. So you would say, on average, beef with a high protein is going to be larger than beef with the low protein, or, heavier. Rats on the beef with the high protein diet are going to be heavier than rats with the low protein beef diet. And that difference, right, on the population scale is going to be in between 2.79 and 38.81 grams. Okay, so that's really that, right? That's that whole process. But I've also, this is a baby of mine. This is what my research is in. But I make these figures, right, of tests to kind of help you see the differences a little bit easier, right? So essentially what this is doing is that if you see a white dot, right, that means there's no statistically significant difference between these two groups, right? So you can kind of trace up and over, right? But if it's filled in, right, there's a statistically significant difference between these two groups, right? Beef and the low protein, beef and the high protein. And we see that here, 0.018. And there's no other statistically significant p-values here, right? So that means that, going all the way back, good Lord, I should put these next to each other. Going all the way back, right? This group and this group are the only two that are statistically significantly different. Essentially, right, like this group and this group are the same, this group and that group are the same, this group and that group are, statistically insignificantly different, if we're trying to be, sort of consistent with the language. But what we're saying here is that the beef with the high protein, statistically significantly different than only this one, right? And this is more likely than not due to this kind of fatter tail down here. Okay. Going all the way back. So we look at this picture, trying to figure out, sometimes, so on the test, hint, hint, wink, wink, you'll get both of these. You could maybe just skip the whole thing, and go straight to this picture, find the black dots, and then go back to like this, right? Okay, so the workflow with ANOVA is, I've also taken this from another class I taught. Get rid of that. We're not reading in any data. It's already done all for us. But you summarize the data based on each group, right? Which is what we saw way back, right? Where we're looking at the group averages, right? Plot box plots, most likely will be done for you, right? So that's easy enough. Then you just create your ANOVA model, right? Or it will be done for you. And that's just going to be whatever thing you are measuring as a function of whatever divides the groups, right? And then based on if your p-value for your ANOVA, right, looks good, if you have evidence to suggest that at least one group is different from all the other ones, then go look at the histogram. Whoops. Go look at that histogram. Look for a normal-ish distribution. If that's good, then you can go on to the next page of results, right? And look for the actual statistically significant difference between the groups, right? Which would be sort of done here, okay? And then after that, you can report your results, okay? So if you need another one, I've got another example here in just a little bit. So I will see you there in a second.